Good afternoon everyone and welcome to this webinar on drought monitoring with Sentinel-2 data. My name is Ewelina Dobrowolska and I will guide you today through this exercise. So first I would like to thank you for attending this webinar today. You are going to learn and explore the possibility to use Sentinel-2 derived water radiometric indices in monitoring surface water bodies in Western Cape province in South Africa. This webinar is going to last about an hour and a half and it is recorded, so after the session will be over, this video will be available in our YouTube channel and on our website, so you can replay it later when you repeat this exercise on your own. So the outline of this webinar is following. I will introduce you first the RUS services and explain how you can access our virtual machines. Then I will introduce you to the study area and explain the drought problem which affected this area in years between 2016 and 2018. Then I will briefly describe the characteristics of Sentinel-2 satellite and its products, and finally I will move to the hands-on case study to show you how this data can be used to monitor changes in surface water extent. At the end of the session, there will be dedicated time for the Q&A, so during the demonstration you can write your comments or questions in the question tab of this GoToWebinar application, and I will go through all of them at the end and try to answer to them. Now, as you might already know, the RUS services stands for Research and User Support for Sentinel Core Products, and it is a project funded by European Commission and managed by European Space Agency, with the objective to promote the uptake of Copernicus Sentinel data and support R&D activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes, pre-installed on virtual machines, which allow you to handle and process the data derived from Sentinel satellites. And what does it mean? With the large amount of data produced by the Sentinel satellites, the challenge is no longer data availability, but rather storage and processing capacity. To solve that, RUS offers virtual machines so that you have the appropriate computing environment to handle the data. Last but not least, we also offer a specialized remote sensing help desk, which is there to answer any questions that you may have about which data to choose, about specific applications of Sentinel data, and so on. And then we also offer dedicated training activities, such as, for example, this webinar. The RUS service is divided into two categories. The first one includes training activities, and the second, individual users and R&D projects. The training activities include face-to-face trainings and virtual classrooms, webinars, and supports to webinars replay, and also support to external training organization and operation. The participants of all the trainings activities can take a possibility and advantage of limited number of remote desktop virtual machines which are accessible to use from any computer. Regarding the individual users and R&D projects, RUS Copernicus provides support to individual projects through a new solution which is a Docker container image, containing the complete RUS virtual environment and tools, and it will be provided upon request. The container can be deployed on users' own infrastructure, which can be cloud-based either in-house or acquired from a commercial provider. But it can also be deployed on a laptop or a PC. The ICT team is available to guide the users through the development procedure, and you can read more information about the Docker on the webpage shown here. RUS is implemented in two portals. We have the RUS-Copernicus portal, where you can find all the information about the initiative, about the availability of virtual machines, and you can also register and request a virtual machine or the Docker container image. Then we also have the RUS-training.eu portal, where you have registered for this webinar, and as well you can find here all the information about our past and future trainings, and for all the webinars you can also find recordings and the Q&A summary documents. Moreover, you can also check our e-learning portal and any news about our training activities. Now, as I mentioned also at the beginning, any recordings of our webinar are also available on our YouTube dedicated RUS Copernicus trainings channel, and you can find them there in a few days after the event. Now that is all for the introduction to the RUS service. If you have any additional questions, please do not hesitate to let us know, and let's now move to the introduction to the topic of this webinar. So the study area is located in Western Cape province of South Africa along the southern west coast. The area has a Mediterranean type of climate, which is characterized by warm, dry summers from November to March and cool, wet winters from May to August. In today's exercise, we will concentrate on the Waterskloof Dam, which is one of the 6 dams located around Cape Town, which form the Western Cape water supply system. The dam we are looking at today is the largest airfield type dam in this water supply system with a capacity of 480 million cubic meters, which is about 41% of the water storage capacity available to Cape Town. The dam mainly serves for municipal and industrial use as well as for irrigation purposes. Cape Town is the oldest and the second largest city in South Africa. You can see in the image here on the right that the water supply system coming from this dam has not kept up with population growth. In 1990, Cape Town had roughly 2 million people. Today, or as shown in this image, in 2017, the Cape Town had a population of about 4 million of people. So the population number has doubled, but the area served by the Waterskloof Dam stayed the same. The topic of this training today is the drought problem and drought monitoring. So Cape Town was hit by a severe drought between the year 2016 and 18, leading to serious water restrictions. Below average rainfall since 2015 have seen the Waterskloof water level drop to critical levels. Water restrictions were imposed by the city of Cape Town in 2016 to meet a target of 600 million liters of water per day, with residents limited to 100 liters of water per day. Rainfall in 2017 remained well below average, and by early 2018 the dam was again approaching critically low level, resulting in water consumption being limited to only 50 liters per person per day, and plans for possible day zero in April 2018, when Cape Town's municipal water supply was predicted to be shut off. As a result of good rains in the winters of 2019 and 20, the Waterskloof water level reached 100% in October 2020. This event emphasizes the need to monitor surface water availability and variability in the areas prone to drought. Here you can see also standardized precipitation index produced by Copernicus European Drought Observatory for Cape Town, which is used for detecting and characterizing meteorological drought. It measures precipitation anomalies at a given location based on comparison of observed total precipitation amounts for accumulation period of interest. And you can clearly see that the Western Cape province area was identified by this index as extremely dry in the period between 2017 and 2018, which corresponds to the period where the dam was shrinking. Now I will move to the Sentinel-2 characteristics. And in this exercise, we would like to use multispectral imagery provided by Sentinel-2 satellite. Sentinel-2 mission carries a passive sensor that is formed by constellation of 2 satellites, Sentinel-2A and Sentinel-2B. They are passing at the polar orbit faced at 180 degrees to each other, and the multispectral instrument it carries has 13 spectral bands in frequencies of the visible near-infrared and short-wave infrared parts of electromagnetic spectrum. The satellite provides data in a cycle of 5 days at the equator. It is characterized by the various spatial resolution based on spectral bands to 10, 20 and 60 meters. The objectives of today's training are as following: the application of different water radiometric indices over drought-affected area, assessment of surface water area changes from Sentinel-2 derived water masks. And for the purpose of this training, we will apply following software. We will use Snap to perform all the analysis. We will apply Sen2 core processor to atmospherically correct our Sentinel-2 level 1C images. Then we will use graph processing tool to automatize processes in Snap. And finally, for visualization purposes, we are going to use QGIS desktop application. Our processing steps will include atmospheric correction of Sentinel-2 products, resampling, subset, band maps and band merge of the water indices which we will produce, and we will use for that graph processing tool. Then we will perform short time series analysis, and finally we will create water area mask based on the water radiometric indices derived before. Okay, and to get started, let's go to our virtual machine to start our exercise. Okay, so now we are in the Linux-based cloud environment, which has very similar structure as your local computer. First of all, if you are not familiar with this RUS virtual machines, you will find pre-installed software here. We have, for example, Snap, QGIS, RStudio, Jupyter Notebook, and other softwares which are ready to use once you request for your virtual machine for the purpose of. Apart from the software, the virtual machine has already its own file manager system to store your data and results, so you do not use your own computer resources to process the data. Everything you do in this virtual machine is stored. So to start our exercise, let's navigate first to our training kit folder. So you just need to navigate to shared folder, which is stored in your desktop. You can also access it from file manager here. We move to share folder, then you go to training, and here you will find training kit with the code name HYDR03 _ Drought monitoring _ Western Cape. You double click on that, and here you will see a structure which is common for all our trainings. You will see here a folder named auxiliary data, then original folder and processing. And let's go to each of them to see what they contain. Here in auxiliary data folder, you will find a QGIS project prepared to visualize the results at the end of this training. You will find also expressions text file, which we will use later. You will find also two Snap sessions, which enable you to open very quickly the products we want to visualize. And here you will find the shell script, which I will also describe later, what it contains. Here also, as the last results, you will get a chance to visualize the changes in the area of water. It is a file stored in CSV format coming from QGIS. Then in original folder, you will see a list of files. We will use, for today's exercise, we will use Sentinel-2A images in 1C level here, downloaded from Copernicus Open Access Hub. I will show you in a minute how to do that. You will find also products metalink file, which enables you to download all those products at once from Copernicus Open Access Hub. And here you will find their unzipped version. In the folder named Level 2A, you will find atmospherically corrected images. You see they are saved in .safe format, and they are output of the Sen2 core processor. I will briefly show you later how to process those images. Okay, now going to the processing folder. Here it is almost empty. It only contains a folder with vectors to display results in QGIS. They are prepared for you, for your convenience, to visualize the results faster without need to process all the data in QGIS. Okay, so to start our exercise, first I will show you how you can download the data from Copernicus Open Access Hub. So you need to navigate to Firefox browser here, you double click on that, and now you see you are redirected immediately to Copernicus Open Access Hub. And to download the data, you just need to go to Open Hub here. And once you have your Copernicus Open Access Hub login and password, you just click here Login. If you do not have the account yet, you just need to click Sign Up, and then you will be redirected to the registration page, and then you can log into Copernicus Open Access Hub. As you know, we are using for this exercise Sentinel-2 products, 16 images, which cover the area close to Cape Town. So it will be more or less here. And they cover this area of this dam. And for now, I will show you just how you can retrieve one product from Copernicus Open Access Hub, not 16, because it will take too much time. As you know, the data we are using today are coming from wet and dry season from 2015 until 2020. And the images are coming from March or April, then from August and December of each year. So to do that, you just need to switch to the area mode first, and you draw the polygon, which covers more or less the area we are interested in. Then here you will see these three lines next to the card icon. You open it, and here you will place your search criteria to filter the images you want to download. So here in the sensing period parameter, you go to the calendar and then you navigate to, for example, 2017, and we want to acquire images from August, let's say, and from 1st. And then go again and narrow down the selection to August again and until 10th of August. Then you need to select mission Sentinel-2. Satellite platform, we know we are going to use Sentinel-2A images. And here we know also relative orbit number. So all images have the same relative orbit. They are coming from the orbit with a number 121. And now we can click search. Now you will see as the output one image pops up. This is the image we are using indeed. It comes from 9th of August. You can expand also to see more details of this image. And what you need to do when you search for the images, if you know that you will be using much more images than one, because if you want to retrieve one product, you just click download here and the download process will start. But if you know that you are going to use several products, you just click here add to the cart, and you can do this when your product is online. So what does it mean that the product is online? Due to ESA policy on the availability of Sentinel data on Copernicus Open Access Hub, and to ensure the continued access to all Sentinel data at all time, the long-term archive has been implemented to roll out the oldest data from the online access. And what does it mean? It means that usually for this area here, the data from the 2017 or from before 2020 are stored in long-term archive. And it means that you cannot retrieve immediately this data, but you need to request for them. And it usually takes several minutes or sometimes hours, and then the product will appear available online. So for example, I can show you on one example the offline product. So if you maybe we will change the dates here and we will select product from let's say from July, and we click search with the same area, And you can see the products are offline, and what you can do to make them online and to make it possible to download, you just click on the download icon. And here you will see the message that offline product retrieval has been initiated. So once it is also stored in your cart, and once it will become available again, it will change the color to white, and then it will be possible to download it. So let's now move to our cart here. You can see I have also other images here stored, but basically what you will do, you will just press here download cart once your products, all of your products are online. You will download it. When you click download cart, then this window will pop up. You just need to select save file and click OK. And now you will see that your product's meta file is downloaded. And where is it stored? It is stored in a RUS folder in this virtual machine. When you go down, you will see the meta file product. And what you will need to do, you will just need to copy and paste it to your training folder here, to original folder. As you can see, now I have it stored already here. And it is important to store it in this folder, because then when you would like to download several products using ARIA to core, which we are going to use today, then all the images will be saved in the path where your product's meta file is stored. And okay, now I can close the Copernicus Open Access Hub. And I will just show you how you would download the files if they were not stored here. So what you would need to do, you just need to open terminal window and write ARIA 2 core 2C and press enter. This tells you that this software is installed already in our virtual machine, and it is ready to use. It also shows you options that you can use this software. And once you see this message, now you need to change the directory. You need to direct this program, this terminal, to our original folder. So you just copy and paste the path here, and you write cd, so change directory, and you paste the whole path. And you, without this... and you click enter, and now you can see that we entered to our original folder. What we need to do now? Now that in this expression file, you just open it with mousepad, and here you will see a sequence that you need to copy and paste to your terminal in order to download the data from Copernicus Open Access Hub all at once from your cart. And what we are doing here? Here we are calling our software ARIA 2 core, which enables to download data from Metalink file. Here with this parameter, you need to insert your username and password, which you use in Copernicus Open Access Hub. Here you need to set also parameter check certificate, and you need to set it to false. Then in the next line you need to also say the maximum concurrent downloads, because Copernicus Open Access Hub allows to download only 2 products at once in parallel. And here we just specify the product's meta file with the name of this file we have in our original folder. And normally you would need just to replace this username and password, and you click enter, and then the processing will start, and all the products will be downloaded to your original file here. But for the purpose of this training, I will not do that. I have already all the images stored. So we can close it now. Okay, so now let's have a look on the images we have downloaded from Copernicus Open Access Hub. To do that, we need to launch Snap desktop application, and you do that by double-clicking on this icon here on your desktop. And now you can see the layout of Snap. So here is the main window where our products will be displayed. Here we have Product Explorer window, which shows all the products loaded into your Snap session. And here you have tabs with several options. You have color manipulation tab, a world view where you can locate your product imported into Product Explorer, and navigation tab, and so on. Here you will also find several functions you can use. You can use a set of tools for raster products, for optical data, radar, and so on. And okay, let's open first the product downloaded. So you go to Open Product here, and we want to open products from our training kit. You double click on that, and here in original file you have all products downloaded. You just need to navigate to the product name, and I will open first the product from 10th of August 2015, and I click open. And now you will see that the product has been imported. You see also its footprint in the world view map. So you can see it is located here in South Africa. What I would like to mention now, it is that the product we have imported is in 1C level. And it means that this product has been radiometrically and geometrically corrected, including orthorectification and spatial registration. However, atmospheric correction is applied only to level 2A data. And this is not our case. The level 2A data were not available for our study site at this time period. So what we need to perform atmospheric correction on all those 16 images downloaded to obtain level 2A product of Sentinel-2. But before I show you how to perform atmospheric correction, I will tell a few words about it. So the solar radiation reflected by the Earth surface to satellite sensors is affected by its interaction with the atmosphere. The objective of applying an atmospheric correction is to determine true surface bottom to atmosphere reflectance values from the top of atmosphere reflectance values by removing atmospheric effects. And atmospheric correction is especially important in cases where multi-temporal images are compared and analyzed, as it is in our case. And in this tutorial, I was using the Sentinel-2 processor to atmospherically correct all the images. You will find also more information about it in our tutorial PDF, but I will just show you how to perform this process in Snap. So Sentinel-2 is a processor for Sentinel-2 level 2A product generation and formatting, and it performs the atmospheric, terrain and cirrus correction of top of the atmosphere level 1 input data. And this processor is built in Snap, so it is ready to use. And to use that, you just need to go to Optical, Thematic Land Processing, Sentinel-2 processor, and Sentinel-2 280 version. You click on that. And one tricky thing about Sentinel-2 processor is that it does not read zip file, even if Snap is able to read that. You need to navigate to extracted file. That is why I extracted previously all the images to .save format. You double click on that, and then you need to navigate to XML file, and you select it. And now it is correctly read by a Sentinel-2 processor. Now you switch to processing parameters. And here you don't change anything. There are several functions that you can change, but for this basic operation to just convert one C product level 2, level 2A, we do not change anything here. We just change resolution because we are interested to have all the bands of the Sentinel-2 product atmospherically corrected. So we choose all instead of 60. And here you need to check display execution output So in this way you will see the progress of the processing. And now you would need to click Run, and then the process will start for one image. The other thing about this processor is that you cannot build it to Graph Builder, so you cannot process several images at once. That is why it takes a lot of time, because in this virtual machine, which has 32 gigabytes of RAM, the processing takes about 30 minutes to complete. So it will take several hours for you to process all the data. And that is why, for the purpose of this training, I stored all level 2A products in our training kit. So I will close it for now. And I close this image here. Okay, so now let's have a look on the images which are atmospherically corrected. So I prepared, for your convenience, the session in Snap. So all the products in Product Explorer will be loaded automatically. So to open session in Snap, you just need to go to File, Session, and Open Session. And you navigate to Auxiliary Data folder in our training kit and select preprocessing.snap and click Open. Now you can see all 16 products have been uploaded to Product Explorer. You can see also they all cover the same area close to Cape Town in South Africa. And once you go, for example, to the first product you expanded, you go to bands, you will find all 13 bands which have been pre-processed or atmospherically corrected in the Sentinel-2 core processor. And here in masks, you will find also information about atmospheric correction or the results of this process. Okay, now I close that. And I will just open the first product from August 10th from 2015. And to do that, you just right-click on the product name and you go to Open RGB image window. And here you will select Natural Colors and click Open. Now you can see our image covers rather big area. We are interested, however, only in this small area here, which covers the dam. So we are interested to see changes over this dam over the drought period, so from 2016 to 2018 and later. And for this, we will create water radiometric indices to extract this water body from the rest of the terrain, because as you can see, the reflectance of the water in natural colors is quite similar also to vegetated areas. But it is much better when you apply, for example, false color infrared band composition. You just click here, you click OK. And now when you go to Window, Tile horizontally, you will see that you can distinguish much better water area in false color infrared, so using the red and infrared bands. But the purpose of today's training is to deliver water radiometric indices and based on that create water mask, which then will tell us how this area changed over the drought period. So, okay, as you remember from my presentation, so Sentinel-2 products deliver data in 10, 20 and 60 meters resolution. And most of the operators in Snap cannot deal with this multi-resolution products. So in order to process later all the images and to calculate water indices, we would need to resample the product to the common resolution. Also, what is important, we will need to subset our image to just concentrate on this area here. We do not want to perform our computations on the whole image because it will take so much computational space and memory on our virtual machine. So to pre-process our data, we will do that in Batch Processing Tool and Graph Builder in order to process all the data at once, because we will use the same parameters to all 16 images. And how you can do that? First of all, you need to navigate to Tools and you select Graph Builder. At the moment, you can see that it has two operators, read and write. Read stands for input data, write it is an output. And to avoid confusion, you just right-click on write operator and select delete. And now this is a graphical representation of the operators used in this graph. And here you will find the parameters which we can set to each operator to process our image. But okay, let's concentrate first on the operators we want to use in this processing chain. So first of all, right-click on this white space to add new operator, select Add, go to Raster, Geometric and Resample. Now we need to connect this operator with the input operator. So you just need to navigate over this read operator box to the right. Once you see this red arrow pops up, you just drag and drop it to Resample operator. And here you can see that you can define parameters for this operator, but we will do that later, not to lose time now. Then we need to add next operator, which is subset, and you right-click again, add, go to raster, geometric and subset. And you connect it again with resample operator. Now our pre-processing chain is almost completed. We just need to add the write operator again. So we go to input output and select write. And this will ensure us that our products will be saved in our computer. And okay, for now we do not change anything. We will change all those parameters later when we upload this graph to batch processing tool. Okay, and now we can save our graph, and we go to Save button, we navigate to our auxiliary data folder, and we change the name of the graph here to graph _ preprocessing, and we leave the extension of .xml as it is, and we save it. We can for now close our graph builder. Now, there are several ways to do multiple images processing in Snap. We can use graph processing tool function, which I will show you later. But we can also use batch processing tool, which is included in graphical user interface of Snap. So first of all, we want to focus on that option, which is maybe easier for the beginning. And to open that tool, we just need to navigate to Tools again and Batch Processing. We select that, and here you will see a window with different parameters again. As you remember, we uploaded all the Sentinel-2 level 2A data to our Product Explorer, and now this tool allows you to upload all the data for the processing here in this input-output parameters. And to do that, you just need to click here, and it will allow you to add opened files. And you click that. Now you will see the file name is XML file, but when you click refresh, then this table will populate with actual data extracted from the file name. So you can see the file name of the product, you see the type, acquisition date. Okay, what is also really important before we upload our graph, that you deselect the option Keep Source Product Name here. When you deselect that, it will tell the program to write our output data and save them under the new name. Otherwise, if you keep that option enabled, then all the data we will create with our processing chain will overwrite the original products, and we want to avoid that. So okay, once you deselect this option, now you can load your graph. So click on Load Graph, and here navigate to our shared folder and our training kit. And here, as you remembered, we stored our graph in auxiliary data folder. Now you can find this XML file called graph preprocessing, and we select that and click Open. And you can see now new tabs appeared, which corresponds to the operators we specified in our graph. So let's go now to resample. As you remember, the 13 bands in Sentinel-2 products do not all have the same resolution. therefore size. Many operators in Snap do not support products with bands of different sizes, so we need to resample bands to equal resolution first. And this operator here allows us to define the size of resampled product. It ensures that all the bands have the same size at the end. And the easiest option is to use reference band from source product. So to resample all the products to the band, for example, band 2, which I know that it is stored in 10 meters resolution. And I want to keep the most details I can from this product. So I will not resample it to 60 meters, but to 10 meters. And okay, now I will leave all the parameters, all other parameters as default, and I will go to subset. And as I told you, we do not want to store all the image and process the whole scene. I want to clip it to the area of interest. And of course, also to calculate the radiometric indices, the water radiometric indices, I do not need all 13 bands to compute this. So I will also subset my product. So I will remove the bands from the source product that I do not need anymore. So for that, to select the bands, the several bands, you just need to click, for example, on band 2, and with Ctrl key on your keyboard pressed, you select other bands. And for the purpose of this training, I will use the band 2, 3, 4, 8, and then 11 and 12. So at the end, I will store only 6 bands out of 13, which also will save a lot of memory. Then we are going to clip our image, so to our area of interest, and you can do it also in two ways. You can clip the image based on pixel coordinates, if you know the exact X and Y position to which you want to clip your whole scene. But in our case, we go to geographic coordinates, and in auxiliary data folder, when you navigate to File Manager, you go to our training folder again, and to auxiliary data folder. And here, as I mentioned to you before, we have this expression.txt file, which we are going to use today very often. And we open it with mousepad. And here you will find a polygon well-known text coordinates for subset. And you just need to mark this and copy and paste it here below this world view map. Important thing that you need to remember to update the polygon once you insert it here. And you can zoom now to our area of interest. You can zoom it. Sorry, I click update again. And here you can see the whole scene of Sentinel-2 product. And here is the subset we are going to use. So you can see that a lot of information that we do not need will not be stored in our final product. Now we can move to write operator. And here you will not change anything in the name of this product. And we will change now the directory to our output products. So go here to this 3 dots. And where we want to store our product is in processing folder and in pre-processing. And now we can select that. And here it is. So now we have all parameters set. Then we can run the process. So click run, and all products will be processed one by one. You can see also here the processing progress. So you can see, for example, that already 5 products are being processed, and this will take about 2 to 3 minutes depending on your computational space and on your computer settings. Okay, now our processing is completed. It also tells you how much time it took to process all the images, and in my case it is 89 seconds. And now, when we pre-processed our data, we can close this window, and you will see in Product Explorer that new products appeared, and we have products from number 17 until 32 that has been processed. So now I close those windows here, these views, and I close also the original products, and to do that I just mark the last original product with Shift key pressed. I click on the first product and then right click on them and select Close 16 products. And now we can actually display the output of this processing chain. So for example, navigate to the product from April 6th of 2016, right click on that and select Open RGB Image Window. And now you can see that you can access a lot of more profiles to display the image in different ways. And for example, let's select Land-Water profile. You can see that this uses near-infrared, shortwave infrared and red band, and we press OK. And now you can see that the water area is displayed we can actually distinguish it much better from the land, from the crops, for example. And we will open, for example, an image from 2018 from March, and we open RGB image window again, and we again select land water, and we go to window, tile horizontally, and now you can see actually already changes in the extent of the dam. You can see that in the same dry season in 2016 there was much more water than in 2018. When we go, for example, to the image from 2017 from August, which is wet season, we open again the land water profile. You can see that the vegetation, maybe it's greener, but actually the dam did not refill with water, and it is much smaller than in 2016, if you can have a look on that. And okay, this we will investigate later when we build our water radiometric indices. And now let me come back to the presentation to say a few words about water radiometric indices we are going to use today. So I will just minimize Snap for now, and I will come back to my presentation. In this webinar, we will use different selected indices to detect and map surface water bodies from the Sentinel-2 datasets. These are widely used indices which are developed to detect water, and you can find also more references in our step-by-step guide, where I included references to the papers that used these specific indices. The Normalized Difference Water Index algorithm was developed by McFeeters in 1996 to detect surface waters in the wetland environments and to allow for measurements of surface water extent. The equation is similar to NDVI, except that it uses green and near wavelengths. Generally, water only reflects in the visible light range, as water has almost no reflection in the near-infrared range. It is very distinct from other surface. Because of this absorption property, water bodies as well as features containing water can easily be detected, located and delineated with remote sensing. In this exercise, we will also use other water indices commonly used in remote sensing applications. The Modified Normalized Water Index algorithm was developed by Xu in 2006 and can enhance open water features while efficiently suppressing and even removing built-up land noise as well as vegetation and soil noise. So it is almost the same as previously described Normalized Difference Water Index, but instead of using near-infrared band, in this case we are using shortwave infrared. And in case of Sentinel-2 data, it will be band 11. Then in 2015, another index has been developed, which uses only near band and red band. So this is basically the combination of Enhanced Vegetation Index and Normalized Difference Vegetation Index. It shows opposite behavior as it uses red band to detect water areas. Areas covered by water are indicated here by the values below 0, so not as in the case of other water indices. However, with the water indices displayed before, they all have common problem to assign good value in mountainous areas and where the shadow is present. So automated water extraction index has been proposed to enhance the detection of water bodies. And we will also use this water index for the purpose of this training. Okay, now having this introduction on water radiometric indices done, we can come back to SNAP. And let's calculate the water radiometric indices which we are going to use today. So to do that, we can close all the views here, and we are going to use our pre-processed product. So we can leave all these products in Product Explorer as they are now, and go again to Tools, Graph Builder, because we again want to perform it in automatic way. But in this case, we will perform processing using bash script, which I will explain to you later. So first of all, we will need to prepare a graph again. So for now, let's delete the write operator as we have done before. We have now read operator, which can stay here. Now we need to go to Bandmaps Operator. So to do that, right-click on this white space, go to Add, Raster, and Bandmaps. And here the first bandmap operator will appear. I connect it with read operator, and with this tool I will calculate the first water radiometric index I want to use. And in this case it will be normalized difference water index. So I will just write a short name of this index, NDWI. And here I will go to edit expression to state the ratio which we want to calculate to obtain this water index. And all expressions used in this bandmaps operator are stored in text file, expression text file, which you can find in auxiliary data folder. And for your convenience, I stored here all expressions which are used for all four water radiometric indices. And so we just need to copy and paste this expression here, for example, for normalized difference water index, and we place it in the expression editor. When you see the message OK, no errors, then you can click OK, and the expression is displayed here. It will be calculated. Now we can add another bandmap operator, which we will add in the same way, which corresponds to the second water index we want to produce. So it will be modified normalized water index. And we connect it again with read operator. We go to bandmaps second operator. It's indicated here with this 2 in the parentheses. And we change the name to MNDWI. And here in edit expression, again, we copy and paste the expression stored in this file. So in this case, we will take band 3 and band 11 to access the water radiometric index. And we click OK. And we will proceed like this other times. So we go again to bandmaps and we combine it. Then here we will calculate our other modified normalized water index. We go to edit expression. Here we will use only near infrared and red band, and we click OK. And the fourth index is going to be automated water extraction index. So I change the name again, go to edit expression, and here I will place this more complicated expression which is used to compute this index, and I click OK. Now, what is important? In order to perform time series analysis, I do not want to store all those bands separately, because the requirement of the time series tool in Snap is to have all the products, all the bands of the products saved under the same name. So, for example, this band will be stored under the NDWI name for all 16 products, and in order to compare them later. And to do that, I will add here a band merge operator, which is stored under raster and band merge. And this operator, when I combine it to all the bandmaps operators, It will allow us to store all the data, all the source bands created in Bandmaps in one product. And then this product will be saved finally to our computer. We do not want to store all the bands separately. And you just need to mark all those bands with Shift pressed. And here we will add the last operator, which is write operator. And I connect it with band merge. And now here you see that we have our product name changed. We will change that later. And here we will leave for now the directory as it is. We will also change that later in our bash script. So once it is ready, you just need to click on Save, navigate again to auxiliary data folder, and we will save our graph under the name, which will be graph underscore WI, which stands for water indices and small s. And we click Save. Now we can close the graph builder, we minimize expressions text file, and now I will explain you in more details what is contained in our graph XML file. So I go to Shared, Training, Auxiliary Data. So now I will show you how the graph in XML format looks like, the one that we saved in Snap. So to open that, you just right click on this file, go to open with mousepad, and here you will see a document. So if you are new to programming, or if you are new to the terminal or the command line interface, you might think that this is a random document that is being created, but I will explain you now shortly that it is not. So here you can see all the operators printed down. So you can see that we have our read operator, which we could find in a Snap graphical interface, the Bandmaps operator, the second operator of Bandmap, third and fourth, and so on, and band merge as well. You can find also write operator, which is our output. And now we will edit this document in order to process multiple images. And to do that, we just need to simply substitute the path to the exact file name as it is in this case. We just mark it and we substitute with the variable, which will be called in our case input. And what is important, you will set the name of the variable with a $sign before the name to the variable. So in XML, you specify the name of the variable with the $sign, and then it is followed by the name. And we will do the same in our write operator. So here in line number 105, you need to substitute this whole path with a new variable, which we will call later in our bash script. And I will assign it a name output. And I will not change anything. Our graph is ready to be processed in batch processing. So we need to save it. We go to File, Save As, and I will save it under the name as it has been assigned before, but I will add a suffix with underscore GPT. And I click Save. Now I can close it. And as I mentioned before, there are two ways to perform batch processing using Snap. The first way is to use graphical user interface and batch processing tool. And the second way is graph processing tool, which we are going to use now. So let me show how this graph processing tool looks like. It is basically used in command line. So you go to terminal window. You just need to type GPT and press enter. Basically now you receive a list of operators available in Snap, and they are mostly the operators which we can find in the graphical interface of Snap. And you also need to be aware that since the RUS Copernicus virtual machines are ready to use, it is enough to write the GPT in the command line, and this will trigger the action to launch the GPT program. But if you are using it on your own computer, where the GPT is not recognized as a command, you have to set it as an environment beforehand. And for example, what I can demonstrate for you is that when you will write GPT followed by, for example, the name of the operator which you will find here, for example, subset, then you write dash and H and press enter, it will return graph in XML format and then all the parameters which you can use to run this operator in GPT. And okay, to run the graph in GPT command line, you just need to write GPT and then specify the path to the graph you want to process. And then it will run. But in our case, as we said before, we want to run the graph in batch processing. So we close this terminal for now. And I have prepared for you a document that allows that. It is a shell script document. And for your convenience, I stored it here in order to avoid any confusion and mistyping. And to open that, you just open it as a normal text file. So you go you right click on this and you go to open with mousepad. Okay, and now I will explain you little by little how this script works and what we have placed here. So first of all, in the first line, we are telling this computer to run bash script once we navigate to this document. Then, in the line number 3 and 4, I specify the input parameters, so I specify the path to our pre-processed products, and I store it under the name path_s2. In the next line, in the same way, I specify output folder for our radiometric indices created, and I will store them in processing folder in the newly created folder which is called WIS, which stands for water indices. And okay, this should be clear until now. Then in the line number 7 and 8, I specify the pattern which all pre-processed images have, so they all are ending with the extension .dim, which stands for the file format from Snap. And as I know that all the products follow this pattern, I will just substitute this old end with the new end, so the new extension will be written to the newly created products, and they will be stored under the name of the extension _WIS, which indicates water indices. And this I will use later. On line number 11, the for loop starts. And what does it mean? Here, with this command, we are creating basically the list of files stored in the folder, in the input folder path_s2, which are characterized by the beginning subset _s2a. Then with the asterisk, we want to tell the computer that then later there is something after this name. And they all end with .dim. So we tell the computer to create a list of products which have the beginning of subset _s2a and are ending with .dim. And now for all these images in this folder, we will extract the date of the sensing time. So as you might remember, we would like to perform time series analysis as well. And to do that, we need to focus on the time actually and to know which bands come from which time period. And to do that, we can extract the time from the file name actually, and this is what we are doing here. So if you navigate to the processing folder, and you go to pre-processing, here you will find out that all the files follow the same pattern in their naming convention. But what we are interested in now is to cut the file name and to split it in such a way that only this part, for example, in this first product 2015-08-10, will be left. So with these two lines, we remove everything what is after the T file, after the T letter here. So we remove all these numbers from the file name and everything what is before 2015. So we remove also subset _s2a and other things. And this is done with these two lines, in line 13 and 14. We will do that for all the images. And then the processing, we are calling the processing graph to be run for all those images. And here we print the actual date of the processing, so we will access the processing time. And at the end of the computation for all images, the date will be printed out again. And here we call the graph, so we call the graph processing tool, GPT. Then we state the path to the graph we want to process. And here with -p, followed by the variable name, we set the variable which we assigned in graph XML file, as you remembered. So we first set the name of the variable input, so -p input, followed by $i, which indicates the element in the list of files to process. And we do the same with output. We write -p and then followed by the name of the variable. Then we assign it a name which will consist of the path to the output folder. Then it will be followed by the sensing time extracted with these two lines above. And then we will assign it also a new extension, so it will end with _WIS. And once it is done, it will be printed and all the products will be processed at once. So okay, now we can close it. We did not perform any changes here, and we come back to our auxiliary data folder. And now we will run the script. And to run the script, it is very easy. You just need to right-click on this white space in auxiliary data folder and you select Open Terminal here. In this way, you will access the shell script directly. And now to run the script, you just need to write sh, which is the shell script, and then you write a script name, so the name of the file which contains shell script. So in our case, you can copy it from here and just paste it. And click Run. As you can see, the processing has started. Now you can see that our graph is being executed and the first product is being processed. Then it comes to the second product and it will last like this for about 2 to 3 minutes until all the products will be processed. And I will speed it up for your convenience that you do not need to wait until the processing will be finished. Okay, once this terminal will come back to the base and will print the path to our directory, you will know that the processing has been finished. It is not running anymore, so we can close this. And now actually we can see the output of this process in Snap. So we go to Snap here. And to display the output products, I prepared for you another session file, so you don't need to insert all the products one by one. So you go to File, Session, Open Session, and here we just select Yes, we do not to store this session. And you select the next file, which is called water_indices.snap, and you open it. Now you can see that products have different name. They have the name which consists of the sensing time _ water indices. So it means that they have been processed actually correctly, and they are stored in processing folder in WIS, and here you can see that they are written in DIM format. So we can close them for now. And coming back to Snap, now when you expand this product, for example, by selecting the first product, you go to bands, you can see that you have 4 different water radiometric indices bands. And if you expand other products, actually they follow the same naming convention, they have the same name. All the bands have the same names in all products. And this was the requirement of time series processing tool which is available in Snap. But first of all, I would like to let you compare different water indices. For example, if you go to the product from April 2016, and if you open all of them by just double click on the name of the band and you go to Window, Tile Evenly, you can see the different performance of this water radiometric indices. You can see, for example, that automated water extraction index is actually giving us very good distinction between the land and water. Here you can see also modified normalized difference water index. NDWI also performs well, and you can see that the other modified normalized difference water index also gives us very clear image on where the water boundary is. And because we are running out of time, I would like to move now to time series analysis straight away. So to perform time series analysis, you just need to go to this time series button here located below the window tool. You just open it, and here you will see that a new tab has been created next to World View. Okay, and actually to see differences in water radiometric indices, we will now navigate to the product from 2016 from April, and we will open Normalized Difference Water Index band. We double click on that. Then we go to the product from 2017. We also open it from 2018. And for example, from 2020, from February, so it is still dry period. And now go to Window, Tile Evenly. And now we can actually compare different values of this index. And how you can print out time series analysis in Snap. Here in this newly created tab, as you can see, you can edit our graph and click on this icon here on the top. Here you will find time series analysis settings. And what you need to do, we have 4 products open in a view, but anyway we can analyze all the products from our list. So all 16 products will be analyzed to see the differences in normalized difference water index behavior. So to add these products, we just click here Add Opened. And here again, as in batch processing tool, you just need to click Refresh to actually get the type and acquisition of the images. And here you will see they are placed in chronological order. We can also rename our graph here, so we can set the name of NDWI in our case, and we click OK. And we click Apply and close the time series analysis settings. Once we close this window, here you can filter out the bands which you want to perform time series analysis on. And in our case, first let's select this band, NDWI, and we press OK. And now with this tool, we will extract the pixel values at a position of our mouse. So as you can see, when we navigate over, for example, this image, which comes from 2020, and we will navigate, for example, to the area over here, you can also see here in View, Synchronize Image Cursors. You can see also where our cursor is located on all 4 images. And so when we move, for example, to the area here, you can see different values of this water radiometric index. And you can see, for example, that from late 2016 until 2019, the pixel value is not recognized anymore as water. As you remember from my presentation, normalized difference water index assign positive values to water, and non-water areas are assigned to values below 0, so negative values. And you can see that between in 2017 and 18 mostly, there has been this period of time where the pixel value has the same value which is below 0. So it indicates that this pixel was not recognized anymore as water but as dried area. And you can go also over all the image and inspect that. You will see also seasonal variations, for example here, but in some cases you can find the pixels which clearly show us the dry period. And you can inspect that for the whole image. You can zoom even more. But now I would like to show you also the other band, the modified normalized water index. So I close those views for now. I will open now the images, this band, which, as you can see, differentiate even in better way the water from non-water areas. And it behaves in the opposite way to normalized water index because it assigns negative values to water, and to non-water it assigns positive values. So I will go again to tile evenly. And now here in this filter band, you just deselect NDWI and you assign modified normalized water index. You click OK. And now when you move again our cursor in the same place, you see that also with this index you can actually see the differences in water pixel values. You can see again, in this case, it is possible to see that in this drought period this pixel value was positive, so it indicates that there was no water at this time. It has the opposite direction, this graph. So it shows the dry area, it shows in positive values, in negative values the water is shown. And if you are interested in, you can also export the graph as a text file or export it as an image to save it for later. Of course, in this case we would also need to rename the graph, but for now I will not do that. As I told you, we are running out of time. So now, when you are familiar with time series analysis, we can close this window. And as a last step, I would like to present you how you can calculate the area of changes in Snap. It is not so straightforward as, for example, in QGIS. For this, I would recommend you to go to our training PDF step-by-step guide, and there you will find all steps on how to assess the differences in the extent of this dam and calculate the area in square kilometers based on the water mask, which we will export from Snap right now. But first of all, how to do it in Snap? I will close the product from 2016, let's say, and I will again tile it horizontally again to see the products. As I told you before, the water values behave in this modified normalized water index in a way that the water has a negative value in this case. And how we can extract the water area, as it is, for example, here, to assess how much of this water area has disappeared during the drought period. So to do that, you just need to select the first image. For example, this is the image from 2020, where the dam already came back to its previous shape, let's say. Go to Mask Manager, and here you will find an expression button. You just press on that. And we are going to create a mask over this water index. So we select the same name of the water index, and we know that water pixels have value here below 0. So we just assign the value like this, and we click open. And now you can see that water area has been indicated in red. We can also repeat this process for those two water areas, for those two images. So I go now again, I assign again a mask value. And now I will click on the third view and go to Mask Manager again and click OK. And now this mask is not being stored, it is virtual mask. So once we close the product, we will not get it. But for now, just quickly to show you how you can perform this, this calculation of the area. Now when you click on this view here, on this band number 14, which is the product from 2020, you go to Raster, Masks, and you select Mask Area. Now this operator will quickly compute the area of this mask. And you can see that this dam is covering about 40 square kilometers in 2020. Now you can go to 2018, go to Raster, Masks, Mask Area, and here you can see that the whole area has been dropped by more than half, so it has now 12.5 kilometers square, which is covered by water. So you can see how much of this dam has shrunk actually during the drought. And unfortunately, you cannot use this tool in batch processing, so you cannot calculate this water extent for all 16 images. We will do it in QGIS. But in order to perform it in QGIS, we need to create water mask for all the images and to store it actually. So we do not want to go to Mask Manager and create this mask one by one, but we want to do it in more automatic way. So this will be the last step of our training. We go to Tools, Graph Builder, and we build the last graph of this training. We will not remove now the write operator, as we will add only one new operator, which is a bandmap again. So go to Raster, Bandmaps, and here you can right-click on this operator and select Connect Graph. This will connect automatically all your graph. Here we will not change anything in the source product. In the write operator, we will set another directory. We will create here a new folder called water mask, water_mask. We select that. And then in bandmaps, what we need to do, we just need to rename this name of the band. So we will rename it to water mask. Here we click Edit Expression. And now we are going to use the last expression stored in our text file with expressions from auxiliary data. We just copy and paste this expression here. And what is it? It is basically a condition statement which says to program that, okay, take all values above and equal to 0 from modified normalized difference water index, then take also all the values from normalized difference water index which are above 0, and then take the second modified normalized difference water index and take the pixels below 0, as in this case, as you have seen, this water radiometric index behaves in different way from all the others. And take the last band, the last water radiometric index which we were using, the automated water extraction index, the pixels with values above or equal to 0, and assign them value of 1. If they not fall within the statement, then assign a value of 0 to these pixels. And click OK. Now we can save the graph. Click Save. We will save it under the name graph underscore water underscore mask, and it will be stored again in XML format. We save it and we close the graph builder. And now we navigate to Tools, Batch Processing, Add Opened Files. We refresh again. Now we deselect again Keep Source Product Name, it is very important, and we load the final graph. We go to graph underscore water mask and we click OK. And now you will see the operator bandmaps and write. And here what we need to change as well is to change this product. We will save it under a format of GeoTIFF in order to be able to read it in QGIS then. So we just select GeoTIFF file and then we do not change the directory and we click Run. Okay, now the processing is completed, so we can close it and we can actually see the newly created water mask. Our product now has the name with the extension underscore bandmap, and it is assigned by default by Snap. And here you can see the extracted, for example, area from 2018 from March. This indicates only the water areas here. It will be the last step we perform in Snap for this exercise. And now let's close it. I will not save anything here. And now you can also navigate to QGIS, and here you will find the project which has been saved for you for your convenience to let you see the changes in the water extent of this water dam. So you go to Project, Open, and you navigate to Auxiliary Data folder. You will find here a file called Drought Monitoring, and you just click Open. Now you will see that based on the mask we created in Snap, we extracted the water areas in QGIS, and you can see here with these lines the actual border of this water dam and how it changed over the years. And what is very important, you can see that with this symbology of the layers, you can see the extent of the dam after the drought period. So in 2020, you can see it is here, the border of the water dam. And here you can see the difference which has been seen from 2018 until 2020. Actually, you can see how much this dam shrunk during the drought period. So in 2017, it reached still this border here, this area, but then in 2018 it decreased significantly. And you can play with these layers because you will find here the water extent from all the years and from all seasons, so you can just switch it on and off to see, for example, here the drastic decrease of the water extent in March 2018. Okay, so this will be the end of this tutorial. Thank you very much for attending it, and I will now close QGIS and I will move to some conclusions and remarks. Finally, some remarks. If you wish to repeat this exercise, you can request our RUS virtual machine on our RUS Copernicus-EU website, or if you already have a machine, you can go to your dashboard and request the webinar tutorial kit with the code of HYDR03. And if you would like to learn more about our future webinars or face-to-face trainings, you can follow us on Twitter, LinkedIn or Facebook. And of course, as mentioned previously, the whole tutorial is recorded and it will be available in YouTube in a matter of few days. Thank you very much for listening. I hope you found this training useful for your applications, and I hope also that you enjoyed it. And I will see you in a Q&A session.